In mathematics and statistics, the arithmetic mean, or simply the mean or average when the context is clear, is the sum of a collection of numbers divided by the number of numbers in the collection. The collection is often a set of results of an experiment, or a set of results from a survey. The term arithmetic mean is preferred in some contexts in mathematics and statistics because it helps distinguish it from other means, such as the geometric mean and the harmonic mean. In addition to mathematics and statistics, the arithmetic mean is used frequently in fields such as economics, sociology, and history, and it is used in almost every academic field to some extent. For example, per capita income is the arithmetic average income of a nation's population. While the arithmetic mean is often used to report central tendencies, it is not a robust statistic, meaning that it is greatly influenced by outliers. Notably, for skewed distributions, such as the distribution of income for which a few people's incomes are substantially greater than most people's, the arithmetic mean may not accord with one's notion of middle, and robust statistics, such as the median, may be a better description of central tendency. In a more obscure usage, any sequence of values that form an arithmetic sequence between two numbers x and y can be called arithmetic means between x and y. Definition: suppose we have a data set containing the values the arithmetic mean is defined by the formula. See summation for an explanation of the summation operator, #. If the dataset is a statistical population, then the mean of that population is called the population mean. If the dataset is a statistical sample, we call the statistic resulting from this calculation a sample mean. The arithmetic mean of a variable is often denoted by a bar, for example as in, which is the mean of the values. Motivating properties: the arithmetic mean has several properties that make it useful, especially as a measure of central tendency. These include, if numbers have mean, then. Since is the distance from a given number to the mean, one way to interpret this property is as saying that the numbers to the left of the mean are balanced by the numbers to the right of the mean. The mean is the only single number for which the residuals sum to 0. If it is required to use a single number as a typical value for a set of known numbers, then the arithmetic mean of the numbers does this best, in the sense of minimizing the sum of squared deviations from the typical value, the sum of. If the arithmetic mean of a population of numbers is desired, then the estimate of it that is unbiased is the arithmetic mean of a sample drawn from the population. Contrast with median: the arithmetic mean may be contrasted with the median. The median is defined such that half the values are larger than, and half are smaller than, the median. If elements in the sample data increase arithmetically, when placed in some order, then the median and arithmetic average are equal. For example, consider the data sample. The average is, as is the median. However, when we consider a sample that cannot be arranged so as to increase arithmetically, such as, the median and arithmetic average can differ significantly. In this case, the arithmetic average is 6.2 and the median is 4. In general, the average value can vary significantly from most values in the sample, and can be larger or smaller than most of them. There are applications of this phenomenon in many fields. For example, since the 1980s, the median income in the United States has increased more slowly than the arithmetic average of income. Generalizations: weighted average, a weighted average, or weighted mean, is an average in which some data points count more strongly than others, in that they are given more weight in the calculation. For example, the arithmetic mean of and is, or equivalently. In contrast, a weighted mean in which the first number receives twice as much weight as the second would be calculated as. Here the weights, which necessarily sum to the value 1, are and, the form of being twice the latter. Note that the arithmetic mean can be interpreted as a special case of a weighted average in which all the weights are equal to each other. Continuous probability distributions. When a population of numbers, and any sample of data from it, could take on any of a continuous range of numbers, instead of for example just integers, then the probability of a number falling into one range of possible values could differ from the probability of falling into a different range of possible values, even if the lengths of both ranges are the same. In such a case, the set of probabilities can be described using a continuous probability distribution. The analog of a weighted average in this context, in which there are an infinitude of possibilities for the precise value of the variable, is called the mean of the probability distribution. The most widely encountered probability distribution is called the normal distribution. It has the property that all measures of its central tendency, including not just the mean but also the aforementioned median and the mode, are equal to each other. This property does not hold, however, in the cases of a great many probability distributions, such as the log-normal distribution illustrated here. Angles. Particular care must be taken when using cyclic data, such as phases or angles. Norvelli taking the arithmetic mean of 1 a degree and 359 a degree yields a result of 180 a degree. This is incorrect for two reasons. Firstly, angle measurements are only defined up to an additive constant of 360 a degree. Thus one could as easily call these 1 a degree and a 1 a degree, or 361 a degree and 719 a degree, each of which gives a different average. Secondly, in this situation, 0 a degree is geometrically a better average value, there is lower dispersion about it. In general application, such an oversight will lead to the average value artificially moving towards the middle of the numerical range. A solution to this problem is to use the optimization formulation, and redefine the difference as a modular distance. See also, average, fra copyright check mean, generalized mean, geometric mean, mode, sample mean and covariance, summary statistics, references. Further reading, Huff, Darrell. How to Lie with Statistics. W. W. Norton. ISBN A978-0-393-31072-6. External links, calculations and comparisons between arithmetic and geometric mean of two numbers. Weierstein, Eric W., Arithmetic Mean, MathWorld.